Okay, a couple more bits we want to do before we actually simulate this. So in the ABD configure, I want to set up some speed limits on the bits here, because you know, when the metal snaps, you know, got quite an aggressive kind of springing action going on. I want it to jump around a bit, but not too much. So on the wood and on the glass, I'm just going to set up a speed max and a speed max, and just set them both to 10. And on the glass as well. So into the speed limit, speed max and spin max. Okay, so that's great for that. And then in this delete, I noticed a bit of a mistake. You can see we've lost those little bits of metal, so I just need to put in big metal there. And let's name this as well. Big metal. Good. And let's name these. So I'll just put active and animated. And I'll just copy that and put it here as well. There we go. Okay, so that's everything ready out there. Let's connect up the collider as well. So into here, into our collision geometry. Let's drop that down there. Okay. Turn that on. Okay, so we can see all of our constraints connected up correctly, which is great. Okay, and while we're working on this, I'm just going to click this brain here, which turns off the simulation, so it's not going to simulate now, right? So let me see. So under solver, under the bullet object, here I don't think we want to do anything. Maybe just turn off the bounce. And then under collisions, yeah, so we want, again, just like before, concave seems to work fine here. But be careful with that. And I'm going to turn off the bounce for that as well. We don't want to ground. We've got this working as a ground, and the gravity is on by default, so that's fine. Cool. Then constraints. So here under breaking thresholds, we're going to do a few bits here. So the constraint names. So we got glue, soft, or hard constraints normally. So I'm going to first of all work on the glue constraints of the glass. Okay, and I'm going to turn this off and use this vex expression. So what I want to do here, so we can type some vex in here to affect those constraints over time. Okay, so what I want to do is kind of weaken the constraints based on the frame, right? So I'm going to make first an attribute, f at strength mult, I'll call it. Okay, so this, I'll give it a capital. Strength mult is a fit. We're going to fit this to the frame. So at frame 5. So from frame 5 to frame 100, we're going to set this from 1 to 0.5. Okay, so this attribute will start at 1, and then at frame 5 it will start to go down to 0.5 when we arrive at frame 100. Okay, so basically I'm going to use this. So on the first frame, the strength of the glass will be 1, and then gradually as the simulation goes through, it will weaken it until at frame 100 the strength of the glass will be half. Basically because I want, you know, at the beginning the glass to hold together, and then just towards the end all of it just to completely break apart. Okay, so this isn't going to actually do anything yet because we've just generated this attribute, but we have to actually apply that to the strength itself. So f at strength, which is, you know, the attribute that we've already generated in the ABD constraint property nodes, times equals, so that means multiply and set to, okay, with the f at strength mult that we just created. Okay, and just double check the spelling that you've got, you know, capital M's and so forth here, because you won't really see an error if that's wrong. But that seems to be fine. So I'm also going to do make another one here, again on the glue constraints of the weak this time. Okay, so this is the, I should have named this weak glass, but we got weak wood, and then weak is just the, if you remember, the glass parts in the middle here. Okay, and for this I'm going to do again another vex expression. And basically with this I want the strength to drop down considerably at a certain frame, so similar to what we did before but not exactly the same. So if the frame is more than 10, okay, so after frame 10 I want the strength to drop completely. So f at strength times equals 0.5. Okay, so with this, every frame after frame 10, the strength will be halved. So it's kind of similar to what we did before, but much more aggressive. Okay, and then make sure we finish the statement. There we go. Okay, so that should be fine. I'm just, double checking spelling and everything, and I haven't missed anything, so that looks fine. And then what else? I want to do some more. So let's make another. Okay, and then for this one, I'm going to be working on the glue constraints and the soft constraints of the wood. Okay, so this will be, yeah, the wood constraints. So this won't affect whatever the wood is connecting to, right? So it won't affect, because remember this group, the wood group, is what I created just after the ABD material fracture. So these constraints are not part of this group, okay? But all of the ones holding the wood together are, right? So I want to set up this distance threshold, 0.04. So whenever these soft constraints are stretched beyond that, then they will break. And I want them to only be able to be broken. So if I hover over this, breaking will only be evaluated, from the specific moment onwards, or frame onwards, right? So 43. So basically I want this to hold together as one piece until frame 43, and at frame 43 is when these two bars are really close together. And that's just to be, I found that this was kind of breaking itself before that, and it didn't behave naturally. So I want it to hold together until a certain frame, and then it's just going to kind of crumple at one point. Okay. So we're still not done here. We're doing a lot of constraint stuff here. So for the, if you remember, we also made a group of the wood in the middle there. Okay. So I'm going to grab that weak wood. Then the connectors wood. So these are the constraints between these bits, and the connectors between the wood and the metal, right? And what I'm going to do with them, and this needs to be, we need glue in there as well, and soft. Okay, we're not using any hard constraints, but it doesn't matter, just to leave that there. What I'm going to do is so before, just now, from frame 43, it's able to break, okay? But at this frame, they will all just be deleted, right? At frame 43, the constraints holding the planks together and holding the planks to the metal, and the bits in the middle, because that's where the metal is going to, pinch it, will just disappear. But it will leave the constraints kind of holding these parts together, and they can break, but they, not necessarily will break. All right. And lastly, we have any group. It probably will include some that we've done already. So like these, where are they? These connectors, but we also have the glass connectors and these small bits, I think. So I'm just going to put connectors with a star. So any of these which stretch beyond 0.1, okay, this is just kind of a safety thing, because I don't want anything kind of hanging, like imagine a piece of glass hanging and stretching away from the metal with, you know, it wouldn't look natural. So if it stretched beyond 0.1, I definitely want them to be deleted then. Okay, so I think that's everything we need in the constraints. Everything else here we don't need. The solver, I think that's done. But one very important thing we do want to do, so any pieces which fall to the ground, I want them to be slowed down, right? So I'm going to jump inside here, right, and generate a pop wrangle. So this is a handy way of slowing down pieces at a certain point. So when they're on the ground or near the ground, I want them, the velocity and the angular velocity, to be reduced considerably, right? So if I take the position, if v at p is less than 0.05, okay, so if the position in y, so I need to specify that actually, p dot y is less than this, and let me just copy this, is more, because you know some pieces will pass through the floor and I don't want them to be affected, more than minus 0.5. So this is selecting any points which are 0.5 up or 0.5 down in y. Then I want you to reduce the velocity, right? So v at v times equals, times equals 0.9, and then the same for the angular velocity. So that means every frame 10% will be taken away from the velocity and the angular velocity of any piece on the ground, basically. So be sure not to forget the brackets here. Close and open for the if statement. Okay, and then let's put I don't know, slow v and w. Okay, and then what I also want to do is, because we're going to have pieces falling through this hole in the floor here, I don't want those pieces to be slowed down by this, right? So we'll use a pop group to set that up, and we'll just make a bounding box, and let me just drop in the size that we've got for this that worked for me. I'm going to make it a height 0.3 and 3 in this size, and then I'm going to move it over 0.7. Now if we maybe have to turn this off, there we go. You can see the box, so anything inside that box I wanted not to be affected by this wrangle. So if I make a name here, not slow, copy that, and then I'm going to use that here. Oh, I've already done it, but you can see I've got a exclamation mark, which means don't, or not slow. So everything not in this box will be slowed down, basically. Okay, so that's fine. Make sure you leave the visualizer there in case you moved it. Come back out, make sure we're on the first frame. Let's drop a RBDIO, and we'll do the same as before. It's much more efficient to cache the points. So we'll do geometry and points, and then make sure we get this rest thing. So what should we call this? This is sim2. We'll put it in another folder, sim2, and this will be the rest dot Bgeo. Okay, save that, and then I want the same here. I'll paste. What's that? I don't know why that's not allowing me copy. I'm trying to paste. That's here. There we go. sim2, and then just not rest. We'll just call this version 1 dot $f3 dot Bgeo, and that should be good to go. So just in case, good idea to click reset simulation whenever you've made any changes inside or above, And then let's come here and save it to disk. There we go, that's all done. Didn't take long at all to simulate. I'm just watching a flipbook of that now. But yeah, it looks good. We got kind of bits of glass stuck to the side of the metal, which I really like. The glass kind of gradually gets weaker as it goes on. You see some chunks holding together, and then they get weaker and just kind of fall apart towards the end. We got the wood holding together until these bits of metal kind of seem to crush it. You know, there's kind of one point where it just kind of almost pops, but not pops, you know, too much. We've got these bits falling through the floor. The pieces on the ground there, you notice they're settling fairly quickly, but not too quickly. You know, it can look a bit weird if they just kind of freeze in place. And we got a few bits flying off. That looks okay, like these. Looks kind of nice. But yeah, generally I'm really happy with how it's turned out.